Now let's review PCA with inner products one more time. So actually we covered this one in PCA, right? So when we talked about PCA and the MDS, then we made some connection between the PCA and MDS. And then we saw that PCA could be rewritten based on the inner product. Okay, so let's follow that one more time. PCA finds eigenvector to maximize this Rayleigh quotient. And then with this, again, W is eigenvector. Okay, then this eigenvector should be in the data space. And this data space can be spanned by the data samples. Okay, so if we don't have data samples, then there's no eigenvector there. Okay, if we have data samples in this one-dimensional space, then eigenvector cannot be out of this line. Okay, if we have only in three-dimensional space, okay, so we have data samples in this two-dimensional space, then we cannot have eigenvector out of this two-dimensional space. Okay, so eigenvector should be in this two-dimensional space. That's what this equation says. The eigenvector should be a weighted sum of data samples. Okay, and then the objective function can be rewritten by this. Instead of W, we can use x alpha. Okay, then we have this ratio, and then alpha is actually the eigenvector of this gram matrix or inner product matrix. Okay, then the projection of x can be given by this. Okay, and then projection of a new point x of t is given by this. Okay, this is what we know from PCA. So now look at this one. B is inner product matrix. Okay, then you know where I'm going with this. Okay, so B is inner product. Then we can use corner function, right? So B is, in this equation, we don't have nonlinear function at all. Okay, so if we have a nonlinear function, then this B will be a corner matrix. Then we're gonna see that, and if we use a corner function instead of just inner product in the features in the data space. Okay, again, instead of applying this inner product in the data space, if we apply this inner product in the feature space with the nonlinear function phi, then we can use kernel instead of B. That is kernel PCA. That's simple. Okay, so in the kernel PCA, we have some complicated equations seemingly, but in the previous slide, I just explained the kernel PCA completely. Okay, kernel PCA is that simple. So we're gonna apply PCA onto the feature space. Okay, again, let's assume that we have a nonlinear function, nice nonlinear function phi. Okay, so after nonlinear mapping, then we have this data matrix. And let's assume that this representation is already centered. And why do we assume that these data samples are centered? Okay, and in the feature space, why do you think these features are centered? When we have some relationship between the data points, then we can draw the figure. Like we know the distance between 3 points. Then we can draw a triangle. Okay, good. But we don't know where it is. Like this one is our coordinate, then triangle would be here, or triangle would be here, right? So based on the relationships, we cannot define the location of this triangle. We can define the shape. So there is ambiguity here. So we don't know where it is, so let's assume that these samples are centered. Okay, so we don't lose any information here. We just put more constraint to avoid any unnecessary ambiguity. Okay, so we have a kernel centering matrix H. This H is exactly the same as in the MDS. Okay, and so we multiply this H matrix both sides, so now we have K tilde. So this K tilde is actually our column matrix. And the column matrix K sub ij, the element of matrix K sub ij is actually the kernel, the function of x sub I and x sub j, which is implicitly this inner product of this nonlinear function. Again, we don't map this data set. Okay, and the projection of y is given by this. Okay, so in the previous slide we talked about this one, and the B is inner product matrix in the feature data space. Now K is inner product matrix in the feature space. Okay, that's the only difference. And again, in the kernel tree, we don't have to define the function phi. Okay, again, the alpha is the eigenvector of K. It's basically the same thing as in the previous slide. And projection of a new point x of t is given by this. So instead of B, we use K here. Okay. Now let's take some example to compare PCA and kernel PCA and the linear PCA. So given these data samples, lots of crosses, and then the PCA will find this line, and then we will project all the data samples into this line. And in the linear PCA, this projection line so are parallel. Okay, so we project this way. But in the kernel PCA, these are projection line. So probably we have something like this curve. So on top of to this hypersurface, we want to project all the data samples. Okay, so this direction and these directions are not parallel. Okay, but in the feature space, they're supposed to be parallel. And again, we don't have this nonlinear function. So in our imaginations, if we find, based on these kernel functions, this is implicitly defined. So if we have this phi, then in the feature space, actually we apply the PCA. Again, kernel PCA is quite simple, straightforward. Map the data samples into feature space, and this mapping would be a nonlinear function phi. Okay, and apply PCA on the feature space. And in PCA algorithm, instead of covariance matrix, we have inner product matrix. So we need the inner product in the feature space. Okay, so instead of applying feature mapping function and the inner product, we just use kernel. Okay, and if we apply the kernel PCA, then we can nicely to this input. If we apply kernel PCA, we can nicely find nonlinear space. So this one is first PC principal component, and this one is second principal component. And in the first principal component, these two are completely separable. Again, in the PCA, we don't use labels at all. We just use some dissimilarity, okay, based on the kernel functions. Because these are close to each other, okay, there is a long distance. So the relationship between this point to the blue dots are not that close, okay? So these are close enough to each other, and these are close, and these are not close. So kernel PCA learns that based on the kernel function, then the first coordinate, the first eigenvector will find a space, a one-dimensional space to distinguish these samples. Okay. And the next one is kernel FD, which is an extension of LDA or Fisher discriminant. Okay, so the logic is quite same. We apply nonlinear function phi. Again, we don't have phi, but in this process, we apply nonlinear function phi, and then apply the kernel trick to LDA. That's it. So we have LDA and LDA objective functions, and SB is defined, SW is defined in this way, and M sub I is defined in this way. Okay, so S sub B is between scatter. Instead, let's calculate these features, this matrix in the feature space. Okay, so instead of just SB, we use SB phi, and instead of SW, we use SW phi, and SB phi is defined by this. So let's just compare this one and this one. It's exactly the same except this phi, which means the class mean on the feature space and the global mean on the feature space. Okay, likewise, look at this one. Instead of x here, we have phi of x. Instead of m sub I, we have m sub I phi. Okay, and m sub I is replaced by m sub I phi like this. Okay, so if we have a nonlinear function phi, then kernel FD will be defined in this way. Good. But again, we don't have a nonlinear function, but instead we have to reformulate this kernel FD based on inner product, and then we will replace that inner product with a kernel. Let's drive a kernel FD. Okay, as before, in the kernel FD, the objective function is defined in this way. Okay, Vt is eigenvector. And as we did in the PCA, we can consider V as a linear combination of the training data. So in this case, linear combination of the training data in the feature space. So we can put in this way. Okay. And then we can replace the equation in the previous slide with the kernels in this way. So V transpose times M sub I phi is, if we rewrite, then we have some terms here. Then if you look at these two equations, we have phi, and we have a transpose. So we have inner product between phi sub x, phi of x sub j and phi of x. So this inner product between these two will be replaced by a kernel function. Okay, and then we put it into this way. And then likewise, phi transpose m phi will be replaced by this. Okay, and the m sub I phi and m sub m phi are defined by this. Okay, and then now we have a dual representation of this objective function, and then we have to find alpha. Okay, and then alpha is a general eigenvalue from this Rayleigh quotient, and m is like this and q is like this. And for 2 class, and this one is quite the same as just a linear discriminant analysis, except this phi, right? Likewise here, except this phi, this one is quite the same as before. And the q looks a little different, but it's a little complicated, so you can check this derivation of q in this file. Okay. And then a new pattern x of t can be projected by this. It's basically the same as kernel PCA.